In the previous unit, we discussed one of the behaviors of electrons as they move through a wire. They heat it up. That idea leads to applications such as toasters and light bulbs. In this video, I want to examine another behavior of electrons moving through a wire, but we need some new tools. This is a galvanometer. It is an analog meter that is sensitive to electrical currents. It was developed in Europe in the early 1800s. We shall talk about how it works later, but for right now, all you need to know is that the needle moves based on the strength of the electrical current put through the device. The numbers on the scale are actually angles in degrees. These instruments can be calibrated to be used as either ammeters or voltmeters. For now, let's say that we're using this device as an ammeter. Here we are hooking up a 9-volt battery to our meter. You can see that when the connection is made, the needle moves to the left very, very quickly. As soon as the connection is broken, the needle returns to the middle. The reason the needle moves so much is that there is almost no resistance in this circuit and there is a very high current. Let's see what happens if I switch the wires on the battery. Now when I make the connection, the needle moves the other way. This is because the electrons are going the other way through the wires. When I reverse the battery connection, I am sloping the wire in the opposite direction. In one orientation, the current is clockwise. In the other, it is counterclockwise. The current has a direction, and this meter can tell us which way the electrons are traveling. The meter can detect currents created in any way. Instead of using the battery, we can use one of our hand crank charge pumps. If I turn the handle one way, we get a clockwise current. If I turn it the other way, it's counterclockwise. Of course, if I quickly change which way I'm cranking the handle, I can set up an alternating current in the wire. This is similar to how the utility company energizes the electrical outlets in the house. Okay, so now that we understand what this meter can tell us, let's look at a new way to create a current. Here I have connected a coil of copper wire to our meter. Notice that the meter does not react at all. But if I bring a magnet near the coil, we do get a current. Notice that as I push the magnet into the coil, we get a current going one way, and when I pull it back out, we get a new current going the other way. If I turn the magnet around, we still get currents, but the directions are opposite. An important thing to consider is that the meter doesn't detect electrons, it detects moving electrons. The copper wire is not empty, it's neutral, but it's full of charges. Normally each well has a ball in it, and we don't know that they are there. Moving the magnet near the coil can't change the net charge on the coil, but it seems to create a slope in the wire of the coil, allowing the balls to roll downhill. Let's look at this from a different perspective. Here is a simple compass. The white arrow points to the north. I'm going to place the compass inside the coil of wire. The compass doesn't change its behavior. It doesn't detect the coil at all. However, if I connect a 9-volt battery to the coil, the magnet does react. This is very important. Before I connect the battery, the coil is neutral. After I connect the battery, the coil is still neutral. Remember, batteries do not supply charges to circuits. What's the difference in the two situations then? When the battery is attached, all the electrons start moving through the wire. That motion of charge creates magnetism. Look, if we turn around the battery, thereby sending the current through the coil in the opposite direction, the compass reacts, but this time it spins the other way.